Okay, sorry, I'm bored, distracted, doing this. So the thing with integration is, so you have just some function. No, yeah, I was just trying to decide. So that's fine, because we're mapping from the real numbers to the real number. So this takes the real number. Okay, technically, we would write this as f from R to R, where you can write x goes to f of x, and f of x is what we're mapping to. But this is just overly formal notation for what we need. So then we assume, let's say, f is in C1. We can take the derivative of it. Yeah, whatever. We just assume we can take the derivative. So we know that the derivative of something is, like, if we have some curve, the derivative will tell us what's the slope at certain points. Like the derivative here would be the slope here. The derivative here would be the slope here. And so this is the derivative came up. First came up by, there's actually debate about it, but there was Leibniz and Newton are the two people who were claiming to have discovered it. Realistically, they both came up with it on their own at around similar times, which seems unrealistic, but has happened before. Such as complex numbers, even. A lot of people were thinking of those, I believe. Yes, yeah. That's whatever, we don't have to go into that. But then the reason people came up with the derivatives was to answer a question. It's like, given a curve. Because when we have like a line, if we have a line, we can say y equals mx plus b. And we can go, okay, that's our slope. That's our slope. If x goes up by 1, y goes up by m. Like, we have a slope for that, but we don't have a slope for this. Because, say, like here, if we go to the right this much, we go up there. But then if we go to the right the same amount, suddenly we're going down. Like, we're not moving. It's not a straight line. But then the derivative is answering, well, how could we describe how fast something is increasing or decreasing? And so then we came up with, well, take a tangent line, so it touches at only one point. We take the slope of that, because that is a line. So we take the slope of that, and that'll kind of tell us in the moment how much it's increasing or decreasing, like how quickly. So it's still giving us a slope. So that's the answer to that question. And the way Leibniz and Newton both did it was they used infinitesimal notation, where infinitesimals are you can think of an infinitesimal as 1 over infinity, essentially. There are numbers in infinitesimal. I forget the standard notation, so I'll just call it dx. Dx is called an infinitesimal. Where you're taking this to be for all x, and so this is poorly written because I used x twice, but it's saying, so this thing is infinitesimal if for any number, for any positive real number, our infinitesimal is smaller, but our infinitesimal is also bigger than 0. So it's basically saying numbers that are smaller than every other number. And that's how you would do that. Like that's how Newton and Leibniz came up with the derivative. We're saying, okay, we take, because you know, you can average a slope of a curve. If you have some curve, you can say go from here to here, and we can take like that slope. So the idea of Newton and Leibniz was, what if we took things that are infinitesimally close together? So their difference is an infinitesimal, so basically 0. And then we can take the slope of that, and that's how we came up with derivatives. And it was actually incorrect the way that they did it. It was not completely formal, and later would have to be redefined with limits, and then later still would be properly formalized using infinitesimals by, I believe, the late John Conway, who died last year from COVID, I believe. Very unfortunate. So yeah, so that's the whole thing. Derivatives, that's how we answer that question. Then there's the natural opposite question of, so say we have some function, I don't know, just random function. We have like x squared. Well, you know, we take the derivative of that, we get f prime x equals 2x. I forgot momentarily, it's 2x, not just x. So if you have this x, and this is our derivative, this tells us the slope. So when x is 1, the slope, in a kind of hand wavy way of saying it, of this graph is going to be 2 times 1, which is 2. So that's the line of sight. But we see that this is just a sum function. Like, we could define a new function. We could just say g of x equals 2x. That's a perfectly normal function. That's its own function. It's also the derivative of this thing. So we're given this. And we go, so this isn't just a function. This is also describing the slope of another function. And this is a very common thing in Earth, where given something, like, we know that something can lead to another thing. For example, with polynomials, we can say that given, like, ax squared plus bx plus c equals 0, given this, we can solve that. We can say x equals negative b plus or minus square root of b squared minus 4ac over 2a. Whatever. That actual thing is not important. So we can do that. But then there's also the backwards question of saying, if we're told like 1 and 2, are solutions to a quadratic so what if we're told that, say, 1 and 2 are solutions to, sorry, that's not written very well, but they're solutions to a quadratic. So we have some quadratic, so some ax squared plus bx plus c, where 1 and 2 give 0. Well, can we reverse engineer to get the polynomial? And yes, we can. We can say, we factor it. X minus 1 times x minus 2 equals 0. We'll have roots at 1 and 2. Let me know this problem. We could also take 2. We can multiply by 3. We can multiply by 13. We can multiply by whatever we want. So we haven't found one answer. We have found a class. Yes, that's the word. I'll use that word. Class. We found a class of answers. So we can say that we have found a unique answer up to scaling by a constant, because everything that has 1 and 2 as roots will be some scalar multiple of that thing that I showed. So we get that, and that's all good. So that's a good natural example of wanting to reverse engineer something. So now we want to reverse engineer this. We say, okay, can we figure out that this is the derivative of something? And So that's what we do. So we do it. And as you probably know, the integral of this is x cubed over 3 plus c. And this plus c is just like that. This plus c is just like this a here. It's saying we don't know exactly what it is, but we've described the important parts basically. We've described what's important. So the reason we have plus c is, so we've x squared. Yeah, we saw that the derivative of x is 2x, right? So 2x is describing how fast this is increasing. And so this curve is like this is f of x. But we could also take, right? We can move it up or down however we want. And it'll still, as long as we've just moved the curve up or down and not done anything else, we haven't squished it, we haven't stretched it, we haven't added any new variables, we've just moved it up and down. It's going to have the same thing. Like, if we have this as a graph, and say this is a line, say the slope is 1. This is also 1. Also, these are all slope 1. It's the same thing, where we can shift up and down, and we'll still have the same derivative. Because that's exactly what the derivative is. It's the slope of these tangent lines. And it doesn't matter if we shift the lines up or down, so it doesn't matter if we shift the entire function up or down. And the way we shift a function up or down is adding a constant. And the reason we just say adding is because if we want to shift down, we would just use a negative. So, adding a negative number subtracts. So we have all this. And so then we have this nice thing. We have this is a derivative, this is this. And that's all good. But then we want to ask ourselves, what is this really saying? Like, there must be something relating this question to this one. And, well, there is. So, first let's look at, say you have a square. Because this is what x squared is. This is x. F of x will give us the area of this square. So then, well, the derivative is what we get by, we add on some little bit, we call this h, and then we get the area of this new square is x plus h squared equals x squared plus 2h plus h squared. And we want to ask ourselves, well, how much did this just increase it by? Like, what did we just do here? And so we go, okay, what did we do? Well, this right here is just increasing it by something. Like, we could add a bigger h or smaller h. Let's see. Well, we want to know the average. So then we divide this by h. Great, all good. And that's, make it this like, yes. We get all this, that's good. Take this, and then we can see right here that, well, if we want to find we want to find the difference, we want to find the bit that is added. So then we want to subtract x squared from the top as well. So that gives us 2h plus h squared over h, which is Sorry. Please forgive me. I forgot how to do basic multiplication. X plus h squared equals x squared plus 2hx plus h squared. We subtract the x to get our average, or not, sorry, to get our change, because we want to just be seeing how much we've added. We get x squared plus 2hx plus h squared minus x squared equals 2hx plus h squared. And then we want to see, like, on average, how much this h has done and increased it by. We divide it by h, and we get 2x plus h. So then we want to ask yourself, okay, well, what is this increasing it by as h gets smaller and smaller? Well, then we're just making h gets smaller and smaller. So we divide until h goes to 0, and we get 2x. And that is exactly the derivative of this. So now we want to ask ourselves, well, can we do that backwards, in a sense? And yes, we can. And the exact same thing, we can do it in higher dimensions. It's just not always as pretty. But so, okay, so this is all good. But what we just saw, though, this was area. This right here is area. What we're finding is area. In fact, what we were just describing is how much area is increasing, right? We were adding this little h and the light, and we were seeing how much the area increased. So then what is this? So then this x squared is not just telling us what x squared is. It's telling us when we have this derivative f prime of x equals 2x. It's telling us this is the area that will be swept out. Like, this is the total area that we'll have covered when this is describing our function. So if we were to graph this, we would say, do this, where this is 2x, and well, let's say this is like a, some point a. Well, what will be the area under this curve? We have a triangle, a right triangle. This length will be a. This length will be 2a. So our area one half times 2a times a squared. So if this is our slope, this is describing our area, which we find exactly like this by taking this thing. But that is this. And then the reason we have scaling up is, like, sorry, not scaling, adding, is what if we had the same function, but we had it lifted like this? Well, now we would be finding, instead, just the area of this triangle, instead of the one base above. We're still just finding the area of this triangle. So that's what we're doing. That's what this thing is. The area in this triangle is the integral of this. So it's the area under the curve. And how more specifically would we describe this is, what if we wanted to ask not just the total area, but say we had, no, I'm going to draw this. This is really not x, but it's the same idea. What if, say, we want to find this area. Well, what is this area? What is this area? It's if we take this entire area, right? We take the entire triangle, and then remove this. So I'll draw this over here. If we have this and this, where this is just me drawing this over here, just so I can do this nicer. That is not even close to it. Not even close to a straight line. So we have this. I want to find the area here, but we only know how to find the area of like an entire triangle. So how would we want to find this? We take this entire triangle, and then we get rid of that. And now we have this. So that's where the subtraction comes from. So if we were to write this more generally, we would say that we have some function f, or f of x, which could be x squared, or could be 2x, could be whatever. We want to find the area under the curve. Well, we only know how to find the area for the whole area from so we want to find the area under the curve from A to B. We want to find the area under the curve in this interval. And the way we would write this as notation, which is just custom, the integral from A to B of fx dfx can also be thought of as we're taking all the little changes, the slopes, and averaging them, and then multiplying them by that. That is maybe a confusing way to think of it, because if you've potentially learned that the average of that this is the average. So this is so integrating can also be thought of as we take the average value and then multiply it by the thing. So then we get like the entire value. Because the average value is really the average height of the function. And then okay, I suppose I've said this, so I should actually explain my thoughts better. So say we have some curve. So that thing I wrote, v 1 over b minus a integral from a to b. And if you haven't seen this, then don't worry about it. But with the speed, what this does is it finds the average value of the function. So let's say like this is a, and like this is b. This nice little trough here. So we have this, but we can't really find this. We find the average height. Say like the average height is like, no, that's not even close to what the average height would be. Let's say we find that the average height is like roughly that or so. It's probably not, but let's say we find that. Well, it's given us the average height. So if we multiply, so this is the average height from A to B. So if we multiply by this, we've got, well, this is our height. This is our line. We get this area. And since this is the average, this will be exactly the area under the curve. So that's another way you can think of it, if that helps at all. But side note aside, we have this. So we have this integral, which is some function, and what this is doing is, well, exactly what I described earlier with triangles, except now it's not just triangles, because triangles are much too well behaved to ask students about. No, I don't know, we have some curve. Ignore that. So a nice curve. Not nice. This is a horrible, ugly curve. I'd never want to see it, but at least well behaved. So now we want to find the area from, say, like here to here. We find the area of the whole thing, which we'd write that as, so we're finding interval from A to B, fx dx. We have, this is B, this is A. So we have this. This is area of the whole thing. This is f of B. Right, that's this whole area. But then we want to get rid of this, right? We want to then erase all this, just forget it ever exists. So we don't want to remember this function. We will remember it only in our nightmares. So then we just have this nice little thing. But what did we just remove? We just removed that. That is exactly what we just removed. So there we have it. This is the sloppily written fundamental theorem of calculus. And this is why it's so important. It's because you're essentially saying we can find the areas under curves, and then we can expand this, because once we find the area of a curve, we can essentially, we have a sheet that we have found the area of it, and then if we want, we can wrap it around things, and because then once we have that, we could say, like we know the area of a thing, so then if we can do this, we can find like the area of a cross section, and then if we have a general expression for the area of a cross section, well, the integral of that would be adding up a bunch of areas, which, if you're willing to believe me, it would then be like volume, because that's kind of what volume is. It's adding up a bunch of little thin sheets, just like what this is really saying, like the idea that Leibniz and Newton had, which they didn't quite properly formalize, but still was a very bright idea for the time, was that if we want to find the area of something, which is not necessarily well behaved, area is the same as adding up a bunch of very thin slices. And then you get these slices thinner and thinner and thinner until they approximate. Because really, if you just add up some finite amount of slices, you're going to have a bit of error. But then you add up infinitely many. That's where the limit comes in, which is where they were left wanting a bit. But we have this. And that's the idea. So an area is like a stack of lines, a bunch of lines squished together, and you kind of add up the length of all of those lines, and you get this area. Similar things to extents, like I mentioned, and if you have a bunch of sheets, like if you have a cylinder, you can take that as adding a bunch of its sheets stacked on top of each other. That'll give you volume. So you have this nice measure, which is very brilliant. It seems obvious once you convince yourself of it, but I mean, it doesn't everything. So yes, that's where this came from. One thing to be careful about is there is, just because all the curves I drew started at 0, this won't always happen. Like for example, if you graph cosine, and that'll look like that. So that will start there, which I actually don't care about. Sorry. But if we graph sine, then well, its integral is cosine. Negative cosine, whatever. Which then, so if we graph sine, I'll just do that. If we have sine, and pretend this is a nice sine, then the value of its integral at 0 is going to be that, which is why we need to be a bit careful. And why we have that. Why do we say this? Because otherwise it would lead to problems, which is why we do anything in math, because it works. Yeah. And this does not lead to a contradiction, because if you take the integral at 0, then you'd have cosine 0 minus cosine 0 equals 0. So it doesn't lead to a contradiction, it behaves nicely. Yeah, it works. Because you can also do things with, I suppose, squares and I'd have to think about that better. Better formalize my thoughts and make sure I actually have them before I do that. But okay, so I hope this. Sorry, this has gone extremely long. But this is, I guess, I've shared some of my some ways that I think about calculus and all these things. I don't particularly like calculus, if I'm being honest, but some of these ideas are quite nice. Yeah, I don't know how you're going to be able to do this, but I hope this is helpful.